When I tell friends that I'm a grad student in computer science, they get really excited. Derek, you're a grad student in computer science. We should do an AI startup so we can get rich and retire early and live on a private island. I don't know anything about AI, actually. Sorry, guys. You can hear about it later today, but I'll tell you about the next best thing, which is Byzantine fault tolerance. If you don't know what Byzantine fault tolerance is, here's an illustration by James Mickens in 2013. So Byzantine fault tolerance, or BFT, refers to a family of protocols where a group of servers, some of which are malicious, try to establish some consistent information about the world over an unreliable network. In such a setting, liveness is very important for security. So there's a lot of non-determinism that happens in these systems. So we, the authors, think that BFT systems are a great target for formal verification. And so our goal is to create a framework to verify and implement BFT systems in general. For this talk, I'm going to focus on how we verify a Dafny library that implements PBFT. PBFT stands for Practical Byzantine Fault Tolerance, and it's a protocol by Castro and Liskov in 1998. Now, this is an old protocol, but it forms the foundation for a lot of modern protocols used in blockchains and in payment systems. One thing we can observe about these systems is that there's a lot of structure, and so it is important for our framework to support a modular development and verification strategy. Of course, Dafny is designed for straight line, currently designed for straight line single-threaded code, and we need to adapt Dafny to a distributed system, so we run into many challenges with modularity. The first challenge is that we need to be able to state and prove liveness properties that are composable. So a liveness property is a property over an infinite execution that something will eventually happen. The second challenge we run into is to model the system's environment. So a lot of proofs of these protocols' correctness depend on assumptions about clocks and message transmission, as well as cryptography. There's a lot of really interesting related work, including some by some of the audience members here today in Rock, and with model checking protocols automatically. I'd love to chat about these after my talk. Contribution we have is Shipwright, a Dafny framework for verifying liveness of Byzantine fault tolerance systems. The Shipwright framework is about 12,000 lines of Dafny code, which gives you a flavor of how complicated it is. And we're able to implement and verify a single view of the PBFT protocol with around 24,000 lines of code. I'll start today by telling you about our approach. So let's start with the simple protocol, which I'll call multicast, or the proposal protocol. In this protocol, we have a bunch of servers, and there's a special server called the leader. It's the leader's job to send a value to all of the other machines in the system. So throughout this talk, I'm going to show you many snippets of Dafny code that might be in small font here, and I'll highlight the parts that are important. The first thing we have to do is specify exactly how a programmer implements code for a node in our system. So on the left, we have a API module, and it defines a function type called run. Run modifies some node state in response to some input from the environment and returns a list of messages to send on a network. On the right is an instantiation of this generic run function for our particular proposal implementation. Now, there are two cases for this implementation. In the first case, leader gets from some local external call a value. And if it hasn't done so yet, it sends this value to all of its peers in the system. In the second case, a node receives a value from the alleged leader. And if this value checks out and it hasn't received another value yet, it saves this to its state. Our goal is to prove a state machine refinement theorem about this code, similar to that in Iron Fleet, which is prior work from Hoblitzel and the rest in 2015. We start with a concrete state machine that models the network and calls into the code that I just showed you. And our goal is to show that it refines an abstract state machine that implements our protocol. So on the left is our state transition system that models our network. We have a network module here that has a function type parameter, the same run parameter as you saw before. And this generic network uses this run parameter to update the state of the nodes as well as the network. We have a second module which instantiates this generic network to our particular protocol. And it does this by setting the run argument accordingly and by instantiating the type arguments to the things in the network as you'd expect. Now, I don't know how to put drawings by James Mickens into Dafny', but I do know how to put a state machine. And so on the right, you have a description of the proposal state machine module. In this state machine, the state is much more simple than the state on the left. And so is the transition function. And in fact, the entire transition function fits on the slide right here. So it's a much simpler object. I'd like to emphasize that we use type and function parameters to support a generic network and then instantiate it for a particular implementation. We use non-ghost functions in Dafny' and not methods because these functions serve a dual purpose. First, they are executable code that can run directly. And second, they can compose with the ghost functions that are used to define our models of the network. All right, there's a lot of interesting techniques in our project. I'm going to skip some and go straight to telling you how we prove liveness. So let's move on to our next example, which is a protocol I'll call a voting protocol. In this protocol, let f be the number of malicious nodes in the system, and suppose there are 3 f+1 nodes in the entire system. Each node sends to all the other nodes some value, and we say that the protocol is done for a node if it's received a set of signatures from distinct signers on the same value. And this is called the quorum, and its size is 2f+1. So what things are live in this example? In order to prove liveness, we first have to define liveness. So we can define liveness to be something that always eventually happens intuitively. So for example, we can say in the network, always eventually a message is delivered, or abstractly, a node always eventually receives a quorum. And we represent these kinds of constraints in Shipwrights as something we call a task. So here's a couple tasks in our network module. The first task is the stabilize task, and the second is the message task. And every state machine specifies a function called a predicate called fair. And so this fair predicate looks at the task, the state, and the transition. And we can see that it's true for the message task if the current transition is a message transition, and we've sent a message but not yet received it. And the stabilized task is fair if we have a stabilized transition and their network is not yet stable. We use this fairness predicate to define liveness in terms of temporal logic. In particular, we give this a temporal interpretation on executions in the way that we'd exactly expect intuitively. The problem we run into is that if we unfold this definition all the way, we realize that we have a definition that involves nested quantifiers over some execution, where an execution is an infinite sequence of states and transitions. In other words, if you unfold this, you get for all tasks and for all numbers k, there exists a k prime greater than k such that fair is true on task, the state at index k prime, and the transition at k prime. Obviously, Dafny' is not great at handling these kinds of statements, and in order to figure out how to deal with them, we need to do a little more high-level thinking. So intuitively, we should be able to show that, suppose we have some arbitrary step, and we have some assumptions on the progress of the concrete tasks in the system. It should be sufficient in order to prove liveness to show that over the same step, the abstract tasks also make some kind of progress. We'll formalize this with something we call a completion measure. So here it's denoted mu. And we associate a completion measure mu with every task and with every state, such that either the fairness predicate is true at that point, or the measure decreases. Now the measure can be a natural number, but we found that it's much more useful to have a general definition. And so we can take any measure that has a well-founded partial order. And you'll see how this is useful, an example of this in a second. So once we've defined a completion measure, we can write down our reasoning principles for proving liveness. So consider some state st and some next state st prime. Suppose that we have that for all concrete tasks C task, either C task happens or the measure decreases. It is then the job of the proof engineer to construct a measure such that for all of the corresponding abstract tasks, AST or AST prime, and for all abstract tasks, a task, either a task happens or this constructed measure decreases. And we verified within Shipwright that this is sufficient for establishing liveness. How does this look like in our voting protocol? So let's look at the abstract task associated with node k receiving a quorum. So because we cannot depend on malicious nodes to have progress, let h of s and k be the set of honest nodes in S that k has not yet heard from. if h is 0, if the size of h is 0, then it doesn't matter what we return because the proof is irrelevant. Our fairness predicate is our fairness predicate is true, and so we're done. Otherwise, we return a pair, and the first element of the pair is the size of h, and the second is the measure for the delivery of a message from node I to node k, and where I is picked arbitrarily from h. We can see how this looks like in Dafny'. So we have some code below here that defines a variable pending. Pending calls this helper function map nodes pending, which I made opaque, and uses that to compute h of s and k. And it returns a partition data structure, which is a special data structure we use to identify subsets of all of the nodes in the system. So once we've computed h of s and k, it's very easy for us to return the measure we want. And so once we have this measure, we have two remaining cases. Either the current transition is the delivery of a message from some node in h to a node in k, and then the first element will decrease, or that's not the case, and so the first element of this pair will stay the same, and the second will decrease. There's a few additional things that are useful to us when we define our refinements. First, it's useful for us to make custom libraries for various abstractions, such as quorums. So on the right here is an expansion of our partition module. And the nice thing that this library does is it helps us prove many useful facts about partitions without having to reveal definitions that are opaque. The second thing that's very useful to us is to have a way to pick something from a set consistently, globally in the whole system, and deterministically, but also arbitrarily. So in order to do that, we wrap the Dafny' neutral face, choice operator, in a ghost function here that's just global, and the output of the ghost function actually only depends on, if we fix the set, the type of the element inside the set. So great. Okay, so now I'm going to talk about decomposition and how we use it to verify a single view. So a view in PBFT is a technical term. It means a single attempt to reach agreement. And so the view consists of 4 message types. So we associate a subprotocol with each message type and refine that subprotocol to some corresponding abstract state machine. And I'd like to point out that 2 of these state machines are the same, so we're actually able to completely reuse the code and proof effort there. So each of these boxes are a specification, which involve our fairness predicate, as well as a few other things. And what we do is we define a combine function that takes in a left specification and a right specification and gives us a composite specification. And we also prove that this combine function is consistent with our notion of refinement. Once we do this, we're able to combine all 4 of our abstract specifications and show that it refines this new specification that we call graded consensus. There's some prior work that refers to such a protocol. So the last thing we have to do is produce an executable implementation. The problem is the bottom of this diagram is not executable. It's the product of 4 different state machines, and that doesn't actually even correspond to anything in physical reality. So our solution, of course, is to create a mechanism to compose 2 pieces of code together. The requirements for this is that it must produce executable code. It must ensure that each piece of code that's being composed has assumptions that are consistent with each other. And the most important requirement is that verification effort needs to scale with the growing implementation size. And this is the most important requirement because if you look at this diagram, this bottommost state machine is the most complicated state machine in the whole system. It encodes the whole network, it encodes the entire implementation, and to prove this refinement is actually pretty tough for Dafny'. So this composition mechanism is actually the most complicated part of our framework. It's about a quarter of the code there. So this is very important for making this tractable. Once we have that, we have all the ingredients we need to do our top level implementation and proof. So we're able to show a refinement from about 670 lines of code, which implement this view, to a spec with about 300 lines of code. When we run the Dafny' verifier on everything in the system, it takes about 4 minutes on a 12-core machine, and we run it through the Dafny' extractor to produce Go code, and call this Go code from a trusted server implementation. Implementation is around 250 lines of code, and that implements things such as signatures, networking, and timing, really the whole server environment. What this looks like is really similar to that in Ironfleet, a top-level event loop that handles local inputs and network packets and timeout events. And as you might expect, the run function shows up for the 3rd and final time in exactly the way we'd expect. So I'm sorry if you were disappointed because you didn't get to learn about AI, but today I showed us Shipwright, our Dafny' framework for verifying liveness of BFT systems. We prove a refinement theorem on a single view of PBFT using completion measures and techniques for decomposing the system. Thanks for listening to my talk.
Thank you. Very nice and clear talk. So asynchronous consensus is not live, but you can prove it live under partial synchrony. So that's FLP. Could you explain how your fairness assumptions assume, like, imply partial synchrony or something similar?
Yeah. So you can use whatever assumptions you want: partial synchrony, asynchrony, synchrony. So if you squint very carefully, proving liveness under partial synchrony is a safety property and not a liveness property. You can prove liveness using these measures we have, and they depend on things always eventually happening. So like reliable broadcast is live, not consensus, but reliable broadcast. And you can prove this using our framework. When you talk about like partial synchrony, which is what PBFT uses, you'll need to, a lot of the complexity in our proof actually is dealing with timing, because PBFT's liveness depends on very specific assumptions about timing. And so our framework is able to encode both of these things as safety and liveness properties, whatever you prefer. And the cool thing about our framework is actually during the refinement, you can convert a safety property into a liveness property if you're able to write a specification in the right way. But I guess to maybe answer your question, if I understood it, we handle basically any kind of synchrony. And this refinement theorem in our formulation of liveness will be able to capture whatever assumptions you'd like to prove for your particular property.
Maybe one last question while we are setting up for the online talk.
Thanks for the talk. You mentioned very briefly in passing that you wanted to be generic over the network model. Can you say why?
Yeah, so the network model is generic. And it's important that the network model is generic for several reasons. One, the network is part of the trusted code base. So it needs to be audited by someone who understands like really carefully what the assumptions are. Two, we need it for our composition theorem for pieces of code. So when you compose two pieces of code, you better not have proven that one piece is live under asynchrony and the other is live under partial synchrony. They need to match. So it's important for us to literally reuse the same network model so that we can write that generic theorem.
Okay, let's thank the speaker again.